In this lesson, we want to talk about the nature of current. And current is the flow or the movement of electrons. Everything starts with the electron. It's no accident that our field is called electronics. Now, this is a model of an atom that was what we knew about 100 years ago. We now know that an atom is much more complex than this, but on the other hand, this is all we need to know to understand what the nature of current is. An atom consists of a nucleus that has protons and neutrons. Around the nucleus are a bunch of electrons. We show electrons as if they are orbiting in circular concentric orbits. That's not exactly true. The electrons are really in states or shells, and we'll talk about that in just a couple of minutes as we go along. Protons have a positive charge. Electrons have a negative charge. There are as many electrons as there are protons, so that most atoms are charge neutral. And the atomic number of an element is the number of protons, and therefore the number of electrons, that that particular element has. Now, these energy shells have capacities. So the first shell has a capacity for 2 electrons. The second shell then has a capacity for 8 more electrons, and so on. It gets a little more complicated as we get farther and farther out in energy shells, but the significant point is that these shells have capacities. So the first element with 1 proton and 1 electron is hydrogen. The second element with 2 protons and 2 electrons is helium. That fills this energy shell. The next element with 3 protons and 3 electrons is lithium. And then in lithium, that third electron would have to occupy the next energy shell out. Now, what's relevant for us is what the outer shell looks like in an atom. And atoms that have a single electron in their outer shell are good candidates for conducting electricity. We intuitively know that copper, silver, and gold are the best conductors. They have the lowest resistivity of all of the elements. They're solid at room temperature, which makes them convenient to work with, and they all have a single electron in that outer shell. Atoms with a single electron in the outer shell tend to be good conductors. Atoms with the outer shell fully populated, like this, are insulators, at least tend to be insulators. And semiconductors, for example, silicon, tend to have their outer shells only half populated. Here we show an atom with only 4 electrons in the outer shell, where there is a capacity for 8. It's not a good conductor, but it's not a good insulator either. Now, when we talk about signal velocity versus drift velocity and the velocity of signals through a conductor, signals travel at the speed of light. Electrons travel, or drift, at a velocity we call the drift velocity. Now, the drift velocity is pretty slow, and in fact, most of us can walk faster than the drift velocity of electrons. So we want to be careful about what we mean by saying that current is the flow of electrons. What we really want to do is think in terms of 1 electron in, 1 electron out. Electrons are identical. So if we have a length of conductor and we stick an electron in one end, then an electron comes out the other end. It's not the same electron, but it's an identical electron. And so that's what's happening when we have signal flow. We can think about it like the desktop toy. Here we have a string of little balls that might represent atoms with electrons in their outer shell. We drop this first ball down. It transfers energy to this one and then to this one and so on through here. And the last ball at the end kicks back out again. Now, this ball, when it's dropping, isn't traveling very fast. But the ball at the other end kicks out almost instantaneously. That's kind of what's going on in a conductor. Here we have atoms in a conductor. An electron comes in, displaces this electron in the outer shell. That kicks over and kicks out this electron in the outer shell. That kicks out over here to some other atom, kicks that electron out of the outer shell, and so on. And out the other end, we get an electron that comes out of the conductor. Now, if we have an atom with low resistivity, the single electron in the outer shell is not very hard to dislodge. It doesn't take much energy to dislodge it, but it does take a little energy to dislodge it and kick it out. And that energy that it takes to dislodge that electron and all the other electrons through here represents a loss to the signal. And that is the nature of resistivity. And therefore, that is the nature of resistance. Atoms that take very little energy to kick the electron out of the outer shell have very low resistivity and very low resistance to conduction. Atoms that require a lot of energy to kick an electron out of the outer shell are atoms that have high resistivity and are not good conductors. Now, let's go through a couple of definitions. First, the definition of charge. 1 coulomb of charge is the amount of charge that's contained on 6.25 times 10 to the 18th electrons. That's a lot of electrons. And 1 amp is 1 coulomb of charge flowing across a surface in 1 second of time. So here's a trace or a conductor. Here's an imaginary plane cutting across there. Here is the planar surface, the cross-sectional area across that conductor. 1 amp of current is 1 coulomb of charge flowing across that surface in 1 second of time. Now, it's interesting to speculate how many electrons are there at that cross-sectional area. And I will tell you, I've tried to do that calculation, and it makes my brain hurt because, among other things, you have to make some assumptions about what the crystalline structure looks like at that cross-sectional area. And depending on how you slice through the crystalline structure, that makes a difference on how many electrons you might count. But for a typical conductor, I came up with an estimate that there are between 10 to the 22 and 10 to the 24th electrons in the cross-sectional area for a standard conductor that we might be using on a trace. That's a tiny fraction of the available electrons. So, for example, if we were running 1 amp of current, we might be using 1 in 10,000 of the available electrons in the available cross-sectional area. If we have 10 amps of current, then we might be utilizing 1 in 1,000 electrons at this cross-sectional area. If we had 100 amps of current, well, then we might be involving 1 in every 100 of the available electrons flowing across this surface. We know intuitively that if we increase the current through this cross-sectional area, the temperature goes up. And that is at the same time we are increasing the fraction of the available electrons. And so the higher the fraction of the available electrons that we are involving in the current flow, the more heat is generated and the higher the temperature of the trace. And that makes intuitive sense, and that's kind of comforting when we look at it that way. Now, here is a fundamental law. Current flows in a loop. Here we have a battery and a resistor. Current can't flow because the loop is open. But here, current can flow because the loop is closed. Current flows in a loop, and there is no exception to this statement. There is no exception to that statement. Now, there's a corollary to that, and that is that every signal has a return. Here's a driver and a trace going down to a receiver. Current can't flow because there's no return path. But if we provide a return path, say through the plane, now signal can flow. So every signal has a return, and there is no exception to that statement. Every signal has a return, and you need to know where it is, because the return signals are what account for most of our signal integrity problems. This is a point that we will be making at several points during the lessons. It's the lack of control of the return signals that account for a lot of the signal integrity problems we have on our circuit boards. So current flows in a loop. There's no exception to that. Therefore, every signal has a return. There's no exception to that. And you need to know where the return currents are, because that's where an awful lot of our signal integrity problems are generated. Now, if current flows in a loop, then we can define a loop area as the physical area within the current loop. Say we have a driver, and there's a trace down to a receiver. The return is on the plane directly underneath the trace. That's a relatively easy kind of geometry to think about. The loop area is the length of the trace times the height above the plane. But since every signal has to have a return, then every signal has a loop area. And that's important because we're going to find out there are certain things like EMI that are directly related to loop area. And we will find later on that one of the most important design rules we have on boards is that we want to minimize the loop area. Now, we've been talking about current. Let's talk briefly about voltage. Voltage can be thought of as the difference in charge between 2 points. So, for example, what's the voltage at point A? Here I have a driver. It has a specified output voltage of 3 volts. I've got a trace going down to a receiver, and I'm picking a point A here at the input of the receiver, and I'm asking the question, what is the voltage at point A? And the answer is, you can't tell, because this is a trick question. And the reason of that is voltage is not a point concept. Voltage doesn't exist at a point. It exists between 2 points. Now we say, what's the voltage at point A? All the time. We say, what's the voltage at the input? What's the voltage at the output? What's the voltage at the power pin? We make that kind of statement all the time. And we sort of intuitively know what we mean. But that gets us into a lot of trouble sometimes, because we're being very careless about what the reference point is. The voltage is not measured at a point. It's measured between 2 points, and we need to be careful when we specify what those points are. For example, here's a driver, here's a trace down to a receiver, here's a return path on the plane. Now if we ask what's the voltage between A and B, well, it's reasonable to say that it's probably 3 volts. The output is specified at 3 volts. Okay, that's probably 3 volts. What's the voltage between A and C? Well, that's probably 3 volts also. But what happens if we have something down here, a component, an inductor in this path? Now, what's the voltage between A and B? Well, that's probably still 3 volts if the current is flowing in a loop this way. But we don't know what the voltage between A and C is, because we don't know what the voltage drop across this inductor is. And if I want to know what the voltage is at point A, well, it makes a difference whether I'm referencing the voltage at A with point B or with point C, because depending on the voltage drop across this inductor, I'm going to get a different answer. Now, here's why this is important, and we're going to see in Lesson 5, this is going to be really important when we talk about ground balance. Here is an illustration of 2 integrated circuits. These are inverting gates. If the input signal here goes up, then the output signal here goes down. If the input signal here goes down, then the output signal here goes up. So let's just say the signal here goes up. That turns off this transistor. that turns on this transistor, that turns on this transistor. That brings this point down low so that A is approximately equal to B. And the current is going to flow from the power supply along this path, down through this transistor, down through that inductor, and back out again. Now, if this switches very quickly from, say, a logical 0 to a logical 1, then this is going to switch very quickly from a logical 1 to a logical 0. We're going to dump current very quickly across this inductor. And let's just say the specified voltage between A and B for a logical 0 is 0 volts. Now, it'll be slightly more than that, but for convenience and for discussion purposes here, let's just say that would be 0 volts. Now, what we want to know at C is this going to be recognized as a logical 0? Well, that depends on the voltage at C with respect to D, because that is the reference for the input, just as B is the reference for the output. So we will know we have a logical 0 if the voltage between C and D is 0. Now, for the moment, we can assume that there's not much current through this inductor, so we can assume that D and E are about the same voltage, the same potential. So at the moment, we can say that this device will recognize a logical 0 if the voltage between C and E is approximately 0. Well, here's the problem. We've got this current flowing down through this path. There's a sudden change in current, so there's going to be a sudden change in voltage across this inductor. And what we're going to have here at A is 0 volts with respect to B, but B is going to jump up with respect to E because of the voltage generated across this inductor. So this input goes up, this output goes down, but the voltage at A is going to be 0 plus whatever is across this inductor as far as it looks at the input with respect to E. If this voltage is fairly large, then this input device won't be able to know whether it's looking at a logical 0 or a logical 1, or if the input is in some uncertainty range in between. Now, we're going to cover this in more depth in Lesson 5 and what we do about that. But the importance right now in this particular lesson is that it's really important when we say what's the voltage at A, the output, or what's the voltage at C, the input, that we understand what we're referencing it to. Are we referencing it to B, or to E, or to D? And it makes a difference in all three cases. One last point. Does current flow from positive to negative or from negative to positive? It was Benjamin Franklin who said that current flows from positive to negative. Remember, he was the kite flyer. And although he was a very smart man, this may be the one time that he was wrong. Current is the flow of electrons, and electrons flow from negative to positive. So, do we have to worry about that? Well, it turns out that in general, we do not. The analysis of circuits and the formulas that we use in electronics and the way we look at circuits in electronics, everything is symmetrical. It doesn't make a lot of difference whether we talk about current flowing from positive to negative or from negative to positive. The one time in my career when I've run into a situation in which that was not true is when I was involved with semiconductor current flow, where it really does matter what direction the electrons themselves are flowing. But otherwise, if we're just analyzing circuits, we don't have to worry about what direction current is flowing. And as an industry, we have continued to use the standard that current flows from positive to negative, even though that's not strictly true. So here are some takeaways from Lesson 1.2. Current is the flow or the movement of electrons. One electron in, one electron out. Current flows in a loop. Therefore, every signal has a return. And that is extremely important, and you need to know where that return signal is. And then finally, voltage is not a point concept. Voltage exists between 2 points, and it is always important to know where we are referencing the voltage we're talking about.